This is lecture number 12 in the ABCs of Communism, the second in our Foundations of Archaeology series. And what we're concentrating on, for those of you who may not have seen number 11, are the archaeological methods and techniques that we use to reconstruct primitive communism. Now, I want to do one thing first, which is why I'm standing up in front of this periodic table. And that is, I need to make some corrections and clarifications, at least, of what I talked about in lecture number 11 with regard to carbon-14 dating. And I'll try to concentrate on the key things that you need to remember in order to understand how it works. Now, first of all, a periodic table shows us really clearly one thing. There's only one thing that makes an element, and that is the number of protons in its nucleus. So we have hydrogen, which has one proton, helium, which has two protons, and that's 99.9% of the known universe. Everything else, all of the other elements, make up a very tiny percentage of the number of elements as a total. On the other hand, they're extremely important to a few of us, those of us who live on rocky planets, because that's where we're going to find most of the material that we live on. Now, the reason the carbon-14 dating works, the reason that McNeish could send that corn cob I was talking to you about to Dr. Libby in Chicago and expect to get a date, was very simple. On this, you'll see the carbon has an atomic number, that is, it has 6 protons in its nucleus. Nitrogen is nitrogen because it has 7 protons in its nucleus. Now, when cosmic rays, which are high-speed protons in this case, strike a nucleus of a nitrogen atom in the Earth's atmosphere, and remember, nitrogen is a high percentage of the Earth's atmosphere, it may knock out one of the protons in the nitrogen nucleus. Then it's no longer nitrogen, it's now carbon. Now, carbon has a stable isotopic number. What's an isotopic number? Well, if the number of protons in the nucleus is equal to the number of neutrons and protons are equal, then it's a stable element. What happens if there are more neutrons in an atomic nucleus than there are protons? Well, if it's got 6 protons, it doesn't matter whether it has 6, 7, or 8 neutrons. It's going to react electrically, that is chemically, it's going to react in exactly the same way, because there's only one thing that makes carbon carbon, and that is the 6 protons in the nucleus. You knock out one proton from the nitrogen, changes it from 7 in the nucleus to 6 in the nucleus, and now we have carbon in the atmosphere. Now, carbon combines with oxygen, and you know, I'm sure, that plants take in carbon dioxide, that is carbon plus 2 oxygen atoms in combination. And to the plant, it doesn't matter whether that carbon has 6, 7, or 8 neutrons. To us, it matters. Why? To us, I mean the archaeologists. It matters because carbon-6, that is with 6 neutrons in it, carbon-12 with 6 neutrons in it and 6 protons, is stable. It won't break down automatically into something else. Carbon-14, on the other hand, which has 6, it's carbon, so it has 6 protons, but it has 8 neutrons. So, it is unstable. And we know that now, and I'll cut short the history of how we got to know its accurate half-life, but we know that it is 5,730 years, plus or minus 30 years. So, if you were to have a gram of charcoal excavated from an archaeological site, you send it to the lab, they count the number of atoms of both carbon-12 and carbon-14 and compare the two. If there's only half as much carbon-14 in that sample as there what is if it had been formed today, then we know that that sample is 5,730 years old. I'm going to stop at that point, because if we go any further, I'm afraid I'm going to get you confused. So that's how that system works. I mentioned briefly to you that potassium argon is used by geologists because one of the potassium isotopes is unstable, and in 1.2 billion years it will disintegrate automatically into that's its half-life, into argon. Now, I'll make one more comment. Notice on the far right of the periodic table, all of those elements are unreactive. Doesn't matter what you do to them, they're not going to combine. This is one reason why those of you who have done welding, for example, know that you have argon tanks. They put the argon gas over the flame that you're shooting onto your metal to prevent the prevent the flame from bringing about an oxidation with the oxygen in the atmosphere of the metal that you're melting. The argon stops that. Okay, enough said on that. I'm afraid to get any further into this without confusing you. But just to conclude this, what we have then is nitrogen being transformed at a relatively constant rate in the atmosphere, some of it into carbon-14. And that is the key thing that we need to have in order to later on be able to put a date on something. It has a limit in terms of its time depth. In my day, we used to think that we weren't going to get much in the way of beyond 35,000 years with any accuracy with the radiocarbon date. Now, where we're actually counting every atom in a sample, this can be pushed back to as deep as 100,000. But that so far hasn't been a really big problem in New World archaeology, because everything we have so far is, except for a few sites in Brazil, is younger than 50,000 years. So enough said on that subject. Now I'm going to stop for a moment and we're going to go take a look at some of the charts in my book, Foundations of Archaeology. All right, now we want to talk mostly in this particular lecture about the way in which we reconstruct the environments in which we find tools and features, artifacts and features. Now, I'm going to use as an example a delta formation such as we have with the Mississippi River, because that's so important and you're familiar with it. Now, you don't have to be in the oil business to know that the Mississippi flows into the
What we're going to do is just start all over again. This has to be at a plane with that lens.
Okay.
Otherwise it looks very distorted.
Gotcha. When I turn the page, I'm going to have to turn the whole book too, but
That's okay. I would just start out with, okay, now on to lecture 12 or something of that nature, and that will give me the cue that I blot out everything else we've done.
now we'll move on to the main topic of this lecture, number 12, which is the environments of deposition and how we reconstruct them. And I've decided to use as an example the Mississippi Delta. You know, I'm sure, that the Mississippi River comes from far northern part of North America and it moves all the way down the continent, virtually cutting it in half and emptying into the ocean south of New Orleans. Well, all deltas, however, work in exactly the same way. This particular chart that we're looking at right now shows, this is in the Appendix B of my textbook, Foundations of Archaeology, that we are using as the subject matter for these lectures on environmental reconstruction and Foundations of Archaeology is the name of the book. Okay, now in that particular chart, what you can see is a side view of how water from a river enters into an ocean or a lake. It's the same principle either way. Think of it this way. That water is coming initially pretty fast. If you have had any experience with the Mississippi River, you know that thing is not only huge, but it's swift. And it's bringing down with it a lot of what we call sediment. Sediment can range from gravel-sized rocks, sand-sized rocks, silt-sized rocks, and clay micelles. Well, what happens to it when it hits the ocean? Well, there's a sudden drop in velocity of the river, and that means its carrying capacity drops dramatically at that point. What falls out first is the heaviest stuff, the gravel. What falls out next is the sand. and then the silt. And then finally, if it's quiet enough, the clay micelles will begin to settle out. Now, what happens, of course, is you build up a delta. And over time, the river is pushed to the right or the left of this big delta, and it starts the same process again. Some water continues to flow over and around the old delta, but that water is now really relatively quiet, and it gives the clay particles, which we call micelles, an opportunity to settle out because they are very fine. Now, more time goes by, the new delta is too big for the river as a whole to go over, and it shifts again. In the last 10,000 years, there have been 5 major shifts of the Mississippi Delta that go all the way from the coast of Florida to Texas. And this is well known to geologists because petroleum geology is the heart of this whole thing. Well, now we're going to stop for a moment so I can change and show you what when this sediment, which is now deposited this way, is compacted over thousands of years, it forms rock. So I'm going to change my photograph, my drawing real quickly, and we'll come back to it.
Okay. You don't really need to announce that. Just quit talking and go.
Okay. This is the one we want to get this time. Over here? Yeah, that'll be perfect. And I'll just use this to keep it out of the way. Keep some of it out of the way anyway. Fuck it. I don't think I even need that. You can get that without that thing over here, I think, can't you?
Mm-hmm.
You tell me when you're ready. All right. After thousands of years have gone by, or millions of years, depending upon the situation, what you're going to have is a lot of weight on top of that original delta, for example, and it is going to compact this stuff into rock. At the bottom of this stratigraphic level, you're going to find that you have gravel and large rocks that were the original ones that fell out. The next layer is going to be sand. Then you're going to get a layer of silt. That's what this chart shows. Then you're going to get a layer of shale. Now, the shale is formed from clay micelles. The sandstone is formed from the sand, and of course you're going to have gravel that form an even coarser sedimentary level at the very bottom. And then the process starts all over again. So what's happened is that this is a reflection of the change of the environment of deposition over that particular spot. When that lobe has really shifted, that Mississippi lobe, then it's going to be really quiet water, relatively speaking, on the top of that sequence, and it's going to be compacted from clay into shale. And so, now, why are we interested in these particular rocks? Because it's only sedimentary rocks which have the capability of being reservoirs for oil and gas. So that's why we know so much about the Mississippi Delta. And what we have there, I know when I first started logging wells off the coast of Louisiana many years ago, that one of the things just strikes out to you is that you got nothing except layers of sandstone and then limestone and then shale. Sandstone, limestone, and shale. Well, the limestone comes from the tiny little animals that live in the top 100 feet of the ocean, and they're constantly dying, of course, and they precipitate down onto the floor, and they are compacted into limestone. Or it comes from coral reefs. The corals are little animals that, as I think you know, probably secrete calcium carbonate as their shells. They die, and new ones are made on top of them, and eventually get a coral reef. Well, limestone, shale, and sandstone are relatively porous compared to igneous or metamorphic rocks. So even when they're compacted into rock, there's space in there for which oil and gas can accumulate. The least likely place for oil and gas to migrate through is a shale because it's so it's so tight that it keeps whatever gas and oil are below it for the most part. Now, there's a little bit of gas or oil molecules that are attached on the surface of a clay micelle, so there's some oil and gas in a shale. And nowadays you hear a lot about fracking these shales. And the reason that they can produce something is because when they were being formed as clay particles precipitating in quiet water into a zone that would eventually be compacted into shale, the clay takes with it a certain amount of... A clay micelle is flat in structure as opposed to a grain of sand, for example. If you were looking at the sandstone in a microscope, you would see that there are a lot of space between each of these grains of sand. On the other hand, the clay micelles have attached hydrocarbons to their flat surfaces, but because they are flat and they fit together just like sheets of paper will in a stack, there's no permeability to speak of. If you want to get the oil and gas out of there, you're going to have to break up that shale and liberate it in that way. And that's what fracking is all about, which is not the subject of our discussion. It's also the reason why you're never going to get very much out of a shale, because when you're only going to get something out of a shale that is immediately available once you've cracked that rock open, but you're not going to get very much more after that. That's why this whole business of fracking to produce oil and gas is in the end a losing economic proposition. But that's not why we're talking about it here today. A sandstone, on the other hand, and a limestone have quite a bit of permeability, especially sandstones. That's what we like to perforate when we're doing traditional oil and gas drilling. Now, sandstones also have an interesting feature that we can identify them on a radiometric log. If you run a tool down a hole, in offshore Louisiana, we used to commonly drill at 30,000 feet. So if you were to pull a tool out of there, you would find on your chart up on the surface where you're doing your logging, you would see that your stylus moves over to the right because it's recording more radioactivity, more potassium, in other words, from we were talking about a minute ago. You can see the potassium on this side of the periodic table has a relatively high amount of in any volcanic rock you have a relatively high amount of potassium, and it gets deposited in the form of sand grains, and that is what's registering on your gamma ray log, for example. Even more of this potassium is in the clay micelles, so they'll shoot over even farther to the right. Your stylus, on the other hand, will move to the left when it hits the limestone because there's virtually no potassium in limestone, even though it has a certain amount of permeability. In other words, we can identify these zones that you see here in the ground as we go. And the point to all of that is that for oil and gas purposes, you now know where you want to perforate. You don't want to shoot holes into any place other than, let's say, it's sandstone. You may have a sandstone that's 1 foot thick. You might have one that's 100 feet thick. The 1 foot is going to have probably far less oil and gas in it than the 100 feet. Our logs will show us that, and the engineers that are in charge of producing this particular well will, perhaps they say, okay, let's take a look at that. Let's perforate that first 100-foot zone and see if we get what we think we're going to get. To do that, you run a tool down a hole. It's called a perforating gun, and everything that goes in a hole is the same. It's cylindrical, and in this case it has scalloped holes. A common way of shooting perforating charges is to have 4 per foot, and they shoot off. It doesn't really matter which direction they shoot into, but well, anyway, they shoot a jet charge in through the steel, cement, and into the formation, and the oil and gas can rush into the pipe rushes to the surface, and you can produce it. That's the way that works. All right, why do we use this in archaeology? Well, it's exactly the same principle that we use to reconstruct ancient environments. Every one of these particular zones was laid down when there were certain kinds of plants on the surface of the ground, and those plants leave behind pollen grains that the water has washed in with the sand, the silt, and the clay. So what we have to do there is to get some of the cuttings from that, say, 100-foot zone and take them to the lab and examine them there under a microscope to find the pollen grains. Now, this is why palynology, the science of pollen, is so important to the oil business, because we know the kind. If this is, say, a deposit from the last 60 million years, we'll know exactly what the environment was when you have 20 different plants of a subalpine zone. You find pollens of 20 plants that only live in a subalpine zone, and you know that that's what the environment was like at the time that zone was deposited in an archaeological site. Or if you were doing in the oil business, when I studied palynology for a year at the University of Calgary in their geology department, we had a pretty good understanding of exactly the kinds of pollen that existed in different parts of the Beaufort Formation in the Arctic Sea, and we were able to identify that, for example, which is very useful information to an oil company, because that would tell you, yes, we do want to perforate this zone for sure, as opposed to another one where you don't have these kinds of already identified plants that are deposited in oil-producing zones. But in our case, what we're looking for is an actual environmental reconstruction of what was the environment like when these people built their camp and chipped their stone tools sitting aside a stream someplace. And if we find it's subarctic, subalpine, well, that tells us what we want to know. That tells us the kind of environment it was. If it tells us that, no, this is a tropical setting, well, then we know that. So that's how we reconstruct ancient environments, largely by determining from pollen grains not only by that, but that's one of the best ways. You get 20 well-known subalpine, subarctic plant species in a 2-inch zone in an archaeological site. You can be pretty sure that that's the environment that it was laid down in. This particular chart shows how you can identify with a considerable precision the kind of plant regime that exists from different altitudes in the area in which you're studying. And now I want to show you how that will be reflected in the stratigraphy of an archaeological site. Now, thousands of years later, an archaeologist comes along, digs in this case, about a 6-foot deep test pit in a site, and you can see the natural stratigraphy here. We talked about stratigraphy last time. There was also cultural stratigraphy in this particular site. I know because this is one of those that we dug when we were at Ice Mountain on an area that was perhaps 100 feet below the road, so we had to climb down there on ropes and rope our equipment down there. And then it was a couple 100 feet above the river, the Stikine River. But one of the nice things about it was that it was one of the few places that you could get 6 feet of deposition in that particular area, where the wind blows sediment away as quickly as it deposits it. So at any rate, we tested this particular site. There was not only visible natural stratigraphy in the walls, but there was cultural stratigraphy there as well. And frankly, I don't recall right offhand which cultural complexes we found, but there were a couple that we were able to identify in there. The important thing is, when we want to know what was the environment at that spot, at that time, when these people who made these microblade tools and these other tools, in another case, lived there, what was the environment like? We take that sediment from one of those visible stratigraphic units, or one of those visible stratums, and we move it to the lab and we subject it to palynological analysis. Now this takes a while, so first of all you have to use hydrofluoric acid to destroy everything in there other than what you want. Hydrofluoric acid will leave just one thing behind, and that's the cellulose, which is what the pollen spores that you're studying and that you're looking for are made of. Now, once you make a slide out of this cleaned up material so that all you've got left on the slide are pollen remains, then you can start and go through there, and you have books which will show you what the pollen of every different one of these species that we were just looking at that live in those environmental zones looks like, and you can identify each of these species of plants precisely, and now you know what exactly the environment was at that time. What are the limitations of this method? Well, all methods have certain limitations, and in the case of palynology, there are pollens which will travel 10,000 miles before they're deposited, pine pollen in particular. On the other hand, pine pollen is easily identified. It looks like a barbell under the microscope. And so you say, well, there should be pine pollen here, but we're not going to make that into a real big item on itself, because we know that this stuff could have blown in from Siberia, for all that matter. But on the other hand, there will be pollen cells in there that could only live in a specific altitude along the Stikine River. So this will help us reconstruct that. So the point is, that's how we reconstruct ancient environments in general. All right, now, what about the tools and the flakes and the blades that we find in these sites? We're going to move on to that next. But before I leave this subject of pollen and its analysis altogether, let me tell you that in the last lecture in this series that we made for this year, it's going to be about Brazil. And I mentioned in there that one of these studies that was done with pollen analysis, or what they call phytolith analysis, on a transit that runs from Manaus to Rondônia. The problem with that was twofold, as you'll see. One is that it's only an 18-inch auger core, and you can get that much deposition in the Amazon in a year. So it wasn't anywhere near deep enough. You would have to have a meaningful auger taken, you would have to go all the way to bedrock, whatever that happens to be. And the other is that the idea that you could find remnants of any kind of agricultural material in there is ridiculous. The only remnants that you're going to have of significance will be pollen, because that's the only thing that can survive, and you have to clean that up carefully with hydrofluoric acid, which they did not do. So the point to that in your lecture number 25, I think, on Brazil, is that I was interested in why the U.S. State Department would care about this particular study one way or another, to the point that they were promoting it. Now, this was, when I first started thinking about it, it was before Edward Snowden told us about how the NSA had picked Brazil as its #1 target for subversion. Today, Brazil has got a very active defense program against U.S. imperialist invasion, because now they know that the U.S. is planning on dismembering Brazil as quickly as they can. So that's why the State Department was promoting that particular study. I knew it couldn't have anything to do with scientific interest, because first of all, the State Department is full of fumble-bums. They don't know anything about science or palynology, so you don't have to worry about that. Okay, now let's go on to the rest of continuation of what we find in these archaeological sites and how we analyze it. Now, this particular chart shows how a certain set of obsidian tools that we recovered, we were able to reconstruct. Now, in order to do this, if you were just an amateur and you dug a hole in the ground and you said, boy, there's a bunch of fragments of obsidian here, and that's probably as much as you would say. Well, in the process of taking a rock in one hand and another rock in the other hand, knocking flakes or blades off of one with the other, we like to think that there are two kinds of detritus that are coming about. That which is called a blade if its sides are parallel and there's a ridge running down the middle of it, which shows that previously other blades had been knocked off of it. If it's just the lines running down the dorsal surface of that piece of detritus are every which way, as are the edges, then we know that there was no particular directionality involved in striking it off. In this particular case, we excavated a site in northern British Columbia that an old Indian gentleman took us to, named John E. Carlick, who unfortunately is passed away, and he was very suspicious of us when we first arrived there, because the only other white men that had ever come in there were trying to find gold or steal something from them, like their beaver pelts or whatever. But after a while, he lived down the road about, not very far, a few hundred yards from the bridge that we crossed the Taltan River on. After a few weeks went by, he realized, well, these gringos or these white men are different than the ones that have been here before. But he had made several trips over there because he thought we were digging for gold. But when he went into this structure they called a fish house that they used to dry fish in, where we had set up a laboratory, and my wife was working on the remnants of whatever we brought out of the ground, he began to see, well, I don't know why, but these guys are after all these little flakes and stones that are all over the place. So we tried our best to explain to him what we were doing, and eventually he got interested in it. So he said, well, you're looking in the wrong place. If you want to find our earliest ancestors, you need to go up on this cliff, which was probably about a quarter of a mile from where we were, as the crow flies. And he said, that's where I was born. And he was 76 years old at the time. So he said, there were 2,000 of us in the village at that time, and we all lived up there in the winter. Well, frankly, I wasn't interested in the historic past. I really didn't. I was looking for something early. I didn't want to do this, but on the other hand, the politics of the situation demanded that I satisfy this old fella. So I said, okay, finally, I said, look, we'll go take a look at it. So we packed up one of the trucks and we moved our equipment up there, and we shot in a few lines and a few pits, 2 by 2 meter pits, squares, and we started digging into it, and guess what we found? This stuff that you're looking at in your photograph. Now this is shows you how the construction, we were able to reconstruct the pattern by which the microblades were created, and the reason we were able to do that is because we carefully excavated every single piece of obsidian that we found in the first 5 centimeters. And I would say that everything of cultural significance was in the first 10 centimeters, and it turned out to be the oldest material almost the oldest material we're going to excavate up there. Now, at the time I didn't know about Professor Kobayashi in Japan and his work on Hokkaido Island. But that was pointed out to me by a fellow graduate student named Knut Fladmark when I got back to Calgary, and it was at that point I realized, whoa, what we have here is clear-cut proof of migration across the Bering Land Bridge. So old John Carlick had done us a really big favor. Well, I knew he'd done us a big favor once we started working up there, but I didn't realize how important it really was. Now, you would normally think that something that's 10,000 years old, which this stuff turns out to be, or 9,500 years old, would be at the bottom of 5 or 6 feet of sediment, even in that area. The problem is, in the far north, there's a lot of precipitation, water, snow, and a lot of wind, particularly in that particular spot, which is blowing up a box canyon. So the deposition of sand and sediment is barely any faster than the rate of erosion. And that's why we were able to find this stuff in the top 10 centimeters. Now, if you take a look at that, what you're going to see is what these Indians started with 10,000 years ago in this particular spot was a finely made obsidian spear point-like tool. We call it bipoint, but think of a spear and a kind of a long obsidian point that you would have on it. What makes this such a highly distinctive technology is that it was from this particular type of spear point. These people then took that spear, and instead of using it as a spear, they knocked off the tip. And I'm going to show you in a moment a photomicrograph of how we can examine what happened on the surface of that tip, which I did. We photographed that back in the lab, and we could see exactly where they had placed a wooden or antler punch and then hit it with another rock and knocked off the outside rim, which you can see in this chart, of that spear point. Once they had knocked off the outside rim, they had a flat platform from which they could begin to strike off microblades all the way through. And that's what they did. And this is a chart of reconstruction that shows you how you can do that. What we have here is a picture of how we use the environmental reconstructions of palynology and geology to show us what kind of environment that existed there 10,000 years ago. And then we also were able to show this way the kind of tools that people made, which in this particular case, because they were made of obsidian, left precise marks as to the way in which all of these things were made. And besides, we had all of the pieces that were made on Hokkaido Island in exactly the same way in Japan, and where they're also made of obsidian, which was extremely useful for us. All right, I'm going to switch now and show you some photomicrographs of what a microscope can do when you focus on the working surface of a stone tool. Now, what we're looking at here is what's called a photomicrograph, or you might think of it as a microphotograph of a working surface where the striations, the white lines that you see there, this is taken through a microscope, show us how this particular piece of obsidian was used. It was used in a cutting way. It's a knife. And the photomicrograph of the surface of that spear point that I was talking to you about a minute ago showed us exactly a concentric number of striations that occur, and you can see in obsidian because it is a glass, when you put a punch against that surface and hit it with a rock or an antler and knock off a piece from it. All of this is left in the ground. 10,000 years later, I come along, pick it up, we take it back to the lab, we look at it through a microscope, and we can see these striations perfectly. Some are made from use, as in this case, other striations from manufacture. Now I'm going to change this picture real quickly so that you can see what, on other kinds of rock than obsidian, how marks of manufacture are left behind, and then we can see them on the microscope. You don't have to have obsidian in order to do these kinds of reconstructions. It just happens to be a very good rock to do these kinds of microscopic studies. Now, here's one that's a grinding stone from the Great Basin, a photograph that was taken by one of my mentors who's no longer with us, Hal Eberhardt, my first professor at the Cal State when I was there. But at any rate, what you see here is in the little circle there on that in that photomicrograph, you see a remnant of the rock that was used to chip this grinding stone into form. So that's another way. In other words, this microscopic analysis of working patterns on tools can encompass any material. It's just that I happen to be concentrating on the obsidian because that's where it's easiest to see. Now, we have a few minutes left, and I had said down the road that if we get a chance, we will talk a little bit about the origin of this particular book. This is the cover of this book. It was published in 1976 by Glencoe Press, which was, at least at that time, a division of Macmillan Publishers. It wasn't the first time that this book had been under contract. A few years earlier, when I was teaching at Boise State University, I had gotten a contract with Rand McNally, and I had flown out to Evanston, I think is where they're just north of Chicago, where their base was. And but we have a problem here. It wasn't too long before Rand McNally realized that they had contracted a book from a Marxist professor. So they wanted out. Well, they weren't the only ones that wanted out of me, so did Boise State, so I had to leave there too. Went back to California. Now, in California, I took this same contract to Glencoe Press. Didn't tell them anything about what had happened out there in Chicago with Rand McNally, because of course that would do the same thing there that it done here. Why is that? Because even though they deny it, the press industry in the United States is completely controlled by ideological propagandists for the U.S. ruling class. And the last thing in the world that they're going to publish of their own is any kind of textbook that gives any kind of consistency to an interpretation of history that has a Marxist orientation. So I had learned that much about the practicalities of how to approach these guys. Now, on the other hand, I had certain things going for me, and one was my appearance. I wore a suit, and I didn't look like their stereotypical idea of what a bomb-throwing communist or anarchist would look like. So I used that to my fullest ability and managed to get a contract pretty quickly from Glencoe to do this particular book. Now, as time went on, everything got up to the point where we were producing a book that I was real happy with, and that so far they hadn't had any political objections to. I was not liking the process. I spent a good year working on this book, just trying to fight with all of the editorial aspects of it, particularly in the art department, where they had their ideas of what they wanted for an archaeology textbook, and I had my ideas of what I wanted for my textbook. I was getting to the point where I was thinking, this really isn't worth it, because in those days they would pay you 15% of the adjusted net, and they adjusted it, and you really never knew how much they were whether what they were paying you was right or not. And all of that has changed now, but at that time that's the way things were. And I had about decided, well, when I get done with this book, I think that's going to be the end of it. On the other hand, professors don't make that much money, so if your textbook is a big bestseller, and we don't know that, of course, until we market test it, then it could be a substantial addition to your regular salary. So I was kind of torn about what I wanted to do. But before I could make up my mind about what I wanted to do, somebody went to, the story was that one of the women that was doing proofreading on certain parts of we were in galleys, right? They had already set up the galleys. In fact, they had already paid a printer to produce 50,000 copies. So they were deep into this project. She went to the editor, a guy named Bill Hushaw, and she said, "Do you know you're publishing a communist textbook?" Poor old Bill, his face must have hit, his jaw must have hit the ground, because he said, "What are you talking about?" And then she said, "Well, I just took a course in Marxism out at my university, and that's what this guy's teaching in this whole book." Well, now he's upset. So he has to go tell the president of the company that what she said. He does. This guy's upset. He's about ready to go to another major publisher, and he certainly doesn't want to go with the scandal of having produced by accident a communist textbook, because that would show, of course, that he's not class reliable and he's kind of stupid. So everybody has an interest in getting on with this project if they can at all. So what did we do? Well, they asked me to produce somebody that would be respectable, that would vouch for what we had here. So I went to see a friend of mine who was a Marxist archaeologist at Cal State Northridge, and named Antonio Gilman. Now, Gilman had a PhD from Harvard and another one from Oxford. So, and besides that, his father was a tenured professor of Spanish literature at Harvard, and that's what he'd grown up in. And he wore a suit and a tie, and he had a short haircut like mine. So he was perfect. And he went up there and he said, "Well, this is cultural materialism, like Marvin Harris." Something like that. I don't know exactly what he said to him because I wasn't there, but as I recall, that was the general pitch. And yeah, similar to Marxism, but it's not the same thing, and it's a respectable view. Well, they wanted to hear this because they already spent the money, and they're in production. That's how we got this book through. There was a few more little things that had to happen in order to get more authenticity to it, but at that time at least there was kind of an underground network of Marxist professors in archaeology that he was able to give them the names of. And of course, then we could get a hold of them on the telephone and tell them, "You're going to get a request to review this particular book, and this is what's going on behind the scenes." So then Glencoe felt they're all right. Well, Bill Hushaw lost his job over this. He decided to get out of publishing business altogether, went up and bought a wine ranch, whatever you call it, where you grow wine up in Northern California. And that was the last I ever saw or heard from him. The president went on out to Connecticut for Harper or whoever it was he was going to, and I never heard from him again, of course, and I'm sure he never wanted to hear from me. Now, in the meantime, the book got published in 1976, as you can see from the copyright. Well, it immediately jumped into #1 spot of archaeology textbooks in the English-speaking world, not just the United States, but Canada, England, New Zealand, Australia. And if you go to worldcat.org now, you'll see there's several hundred libraries worldwide which have copies of it. Now, they, as scared as they were about Bolshevism, on the other hand, they're capitalists. And, they'll cut each other's throats for a buck. So they're thinking, Jesus, we got to get this guy to write some more books for us. So I signed 5 more contracts with him. One day got a $10,000 advance. And I didn't really want to get into this, frankly, because I'd had such what I consider to be a bad experience trying to get the first one published. But on the other hand, I could use the $10,000, which was a lot more in those days than it is now. So, well, what happened after that is I got arrested in Peru, and I spent 3 years in jail down there. And by the time I got back, I really didn't want to bother teaching school or writing any more textbooks, and they really didn't want to bother with me either anymore. So they dumped what they hadn't already sold on the university scene, and now you got libraries all over the United States which have copies of this book in it for that reason. Well, at any rate, that's kind of the backstory on this. What does that tell you, though, about freedom of the press in the United States? What it tells you is that you probably already know. That's all nonsense. No such thing exists. They police these textbooks so carefully that at one point they had me writing a textbook for junior colleges, and I had to write, couldn't be one sentence in that textbook which was longer than 14 words. So I had to take my whole manuscript and go break up every single sentence so that, and of course I was pretty verbose in those days, so those sentences were actually had to frequently be broken not only in half but into several parts. All of this was leading me to think that I don't want to do this anymore. On the other hand, I was thinking these guys, they know what they're doing in terms of selling books. So if that's the level at which these kids in junior college can read and comprehend, that's important information for me to know. And it was useful to me in later years, as for example in the production of this book, the ABCs of Communism 2014, or in this case the new book coming out is ABCs of Communism, Bolshevism 2015. So I learned that I have to, for this kind of purpose, I've got to popularize it. I've got to make it fairly easy to read. So all of these are lessons that came out of that initial experience in Beverly Hills, which overall was culturally an enjoyable experience. We were right down the street, about a block away, half a block, from one of the finest French restaurants at that time in West Los Angeles. We were straight away from Robertson Boulevard, went right up next to, of course, into Beverly Hills and Hollywood Hills, areas that I already knew pretty well from my early years. I knew a lot of people up there, so one thing led to another. I didn't mind going there. I didn't mind working on that kind of a book, and I kind of liked the environment. And anyway, that's something I wanted to conclude. I wanted to add that to this series at some point or another. Why do they pay so much attention to archaeology and social sciences? Well, isn't it obvious? They don't want Marxism to get into anybody's mind in this country. Marxism is a theory of science, of culture, and social evolution that they don't want. What they want to publish is anybody that will write anything that says that human society is too complex to understand. That was the way in which American anthropology was reformulated after the death of Lewis Henry Morgan. After Karl Marx had done him the favor of incorporating him into world Marxism, then American capitalist class didn't want anything to do with Morgan anymore, even though he had founded the science of anthropology in this country, in fact in the world. So then he was blotted out for a long time in favor of these guys like Franz Boas, Margaret Mead, Ruth Benedict, the one thing they had in common was we don't know anywhere near enough to write laws of history. Human society is too complex to understand, blah, blah, blah. And that's the kind of line that was published up until the whole country was shaken up by the anti-Vietnam War movement and the concomitant civil rights movement in the United States. And a man named Marvin Harris produced a book called The Rise of Anthropological Theory, where he said Loy, who had written the first ethnological theory book, had said that American anthropology had arisen entirely independent of Marxism. And what this author now did was to show that, Marvin Harris is his name, that he says, in fact, American anthropology has arisen in a direct response to Marxism in every respect. And he went on. He wrote a chapter called Dialectical Materialism in his book, where he says this is where Marx and Engels discovered the laws of history. Now, to a Marxist, if you read that particular chapter, the first thing that strikes you in your mind is Harris doesn't have the slightest idea what he's talking about. What he's talking about dialectical materialism. What he's talking about is historical materialism. But in 1968, when that book came out, it was a revolution in terms of introducing Marxism as such to the graduate students all over English-speaking world. First time they realized that it was Karl Marx and Friedrich Engels who had founded anthropology and had discovered the laws of history. Now, dialectics is a school of philosophy that they used in their day to get to historical materialism. But dialectical materialism and historical materialism are two completely different things. And we'll be talking about that more. We already talked about it a little bit in this series, and we'll be talking about it more as we go along. But that also shows you that a book can have a tremendous impact on thinking people. I'll stop there for now. I have another lecture or two that we want to give on the foundations of archaeology, which will help you understand primitive communism, but we're going to stop there for now.